Hey, in this video we're going to be trying to find the moment of inertia of a cylinder about the z-axis, and here we are told that the density is constant, it's equal to d, the radius of the cylinder is capital R, and the height is equal to h. So we have the cylinder, and this becomes our solid. And since we're dealing with a cylinder, it makes sense to use cylindrical coordinates. And in fact, whenever you have a solid whose projection on the xy plane is a circle, like see here the projection of the cylinder is a circle on the xy plane, it's probably going to be easier to use cylindrical coordinates. So whenever you have a solid whose projection on the xy plane is a circle, I recommend using cylindrical coordinates. Okay, so the moment of inertia about the z-axis is equal to the triple integral over the region R, distance from the axis, which is x squared plus y squared, then we have density, and we are integrating with respect to the volume. Now let's convert this to cylindrical coordinates. So x squared plus y squared, that's going to be r squared, density is equal to d, and dv is going to be r, dz, dr, d theta. Now since density is a constant, we can take it outside of the integral, and now we're integrating density, triple integral over the region r, r squared times r is going to be r cubed, and that's dz, dr, d theta. Now we need to set up the limits of an integration. So if you look at the limits of integration with respect to z, you sketch arrows in the positive z direction, see that z ranges between 0 and h, because this height here is h. Then we find the limits with respect to the radius. You look at the projection of the shape on the xy plane, it's going to be a circle, so the radius is going to range from 0 to capital R, and since it is a complete circle centered at the origin, theta is going to go from 0 to 2 pi. So now we can integrate moment of inertia about the z-axis. It's going to be density times the triple integral from 0 to h, 0 to r, 0 to 2 pi, r cubed, dz, dr, d theta. So if we integrate r cubed with respect to z, you're going to get r cubed z, evaluate at 0 and h. It's going to be h r cubed. It's density 0 to r, 0 to 2 pi, h r cubed, dr, d theta. Now if we integrate h r cubed with respect to r, you're going to get r to the power 4 divided by 4, ranging from 0 to capital R. It's going to be h capital R to the power 4 divided by 4. It's equal to the density from 0 to 2 pi, h r to the power 4 divided by 4 d theta. So that's going to be h r to the power 4 divided by 4 times density times 2 pi. And this is the moment of inertia about the z-axis. Now if you check any source or you go online and find the moment of inertia of a cylinder, you're going to find it written like this: half times mass times r squared, and this is exactly the same thing. And let me prove it to you. So if you rearrange this, first this 2, get the 2 here, we're gonna get h r squared times pi times r squared times d times half. So that's exactly the same thing, I just rearranged it. So we see here you have h r squared pi, that's the volume, and d here, that's the density, and we know that the density times the volume is equal to the mass. And then we have r squared, that's the distance from the z-axis, and we have half, so that's equal to half m r squared. So that's exactly the same thing. So that's it. If you have any questions, please leave them down in the comment section below, and I'll be more than happy to answer them.